Hello and welcome back once again. So, we have been discussing about the fatigue behavior of metal matrix composites, and in the last lecture we talked about the stress controlled fatigue. In this lecture we are going to discuss about the strain controlled fatigue of aluminum based MMCs. So, when we talk about strain controlled fatigue, we can consider two scenarios. One, total strain life behavior, and the other plastic strain life behavior. So let us first talk about this total strain life behavior, where the fatigue data is plotted as strain versus number of cycles, or rather total strain versus number of reversals to failure, which is also written as 2n, and one cycle is 2 reversals. Okay. So here the total strain is the controlled variable, or the total strain can also be considered in terms of the strain that is reached after the stabilization has occurred in a stress controlled test. Okay. So in such scenarios, in this total strain controlled fatigue, it is generally found that the fatigue resistance of discontinuously reinforced MMCs, that is DRMMCs, is inferior to that of the unreinforced material. For example, you can take the same composite that we discussed before while discussing about the stress controlled fatigue behavior, that is that 2080 aluminium alloy reinforced with 15% silicon carbide particles. Okay, so if you recall, this is how the fatigue behavior looked like under stress controlled fatigue test. Now, if you take the same composite, this 2080 aluminum 15% silicon carbide particles, and see the fatigue behavior under total strain controlled fatigue test, then it will look like this. So here the y-axis is strain amplitude, which is plotted against reversals to failure. So for this material, in T4 condition, the fatigue curve would look like this in comparison to the unreinforced alloy. So here you could see that the unreinforced alloy, that is without any silicon carbide particle, is having a better fatigue resistance compared to the composite having 15% silicon carbide. Okay. So this is what I said in the beginning also, that under such total strain controlled fatigue tests, the composite will show an inferior fatigue resistance compared to the unreinforced matrix. Okay. And here you can also see that the differences are more pronounced at high strengths. So the inferior fatigue resistance of the composite compared to the unreinforced matrix material under total strain controlled fatigue can be explained as follows. So if you recall, the total strain range, that is epsilon T, is equal to the sum of the elastic strain and the plastic strain. Okay. So now, due to the higher elastic modulus and lower proportional limit of the composite, the elastic strains are much lower in the composite compared to that in the unreinforced matrix material. Okay. So now, since it is total strain controlled, if the elastic strain is reduced, the plastic strain has to be increased, right, according to this particular equation. So therefore, the plastic strains in the composite will be higher compared to that in the unreinforced matrix material. So this increased plastic strain will dominate the fatigue damage in the composite material, leading to a lower fatigue resistance in the composite. And as I said before, this difference in the fatigue life is most pronounced at high strengths, and this is primarily because of the lower cyclic ductility of the composite, which leads to a decreased ability to resist plastic strain accumulation, and therefore it will lead to early failure. Okay. So this total plastic strain can be also graphically represented if we look at the stress strain loops which develop during this kind of fatigue tests. And we can again take an example. So let's take this alloy and its composite, this aluminium copper alloy. And let's look at their stress strain loops and see where is the plastic strain more, whether it is in the alloy or it is in the composite. So this dotted one is for the unreinforced alloy and the solid curve is for the composite. And the total strain is this one. So it's a total strain controlled fatigue behavior that we are talking about, and therefore the total strain in the composite will be equal to the total strain in the unreinforced material, that is delta epsilon T composite is equal to delta epsilon T unreinforced matrix. But let us see where is the plastic strain more, whether it is in the composite or it is in the unreinforced matrix material. So here is the plastic strain for these two materials. This one is for the composite and this is for the unreinforced matrix. Okay. So here you can clearly see that the plastic strain in the composite is greater than that in the unreinforced material. Okay. And therefore, according to this particular equation of strain life behavior, that if the elastic strain is less in the composite due to its higher elastic modulus, the plastic strain has to be higher. So that's what you see over here also in the stress strain loops. And similar to the mean strain effects that you see under constant stress conditions, mean stresses may also develop under constant strain controlled conditions. So therefore, if you look at the stresses developed in the composite and in the unreinforced material, the stresses in the composite will be higher compared to that in the unreinforced matrix at a given strain. Okay. So this leads to a higher fatigue damage, particularly at high strains, and that is why you see the most pronounced differences in the fatigue life at high strains, as you could see from this particular figure over here. Okay. Now let us talk about the plastic strain life behavior. So here the plastic strain is the controlled variable. Although there is not much data available for composite materials under such conditions, but still we can take some examples and see how a composite material behaves in comparison to the unreinforced material under plastic strain controlled fatigue tests. Okay, so we can consider this alloy 2219 and it's a composite reinforced with 15% spherical TIC particles. So here also it has been found that the fatigue life of the composite is much inferior compared to that of the unreinforced alloy. In fact, for this particular composite, it was found that the fatigue life is decreased by a factor of 2.5 to 10 in the artificially aged condition. Okay. So if we plot the plastic strain amplitude against the number of reversals for this particular material, it will look like this in comparison to the unreinforced alloy. So here it is plastic strain on the y-axis, and x-axis of course is the number of reversals, that is 2n. So here the unreinforced matrix lies somewhere here, and the composite is somewhere around here. So this upper one is for the unreinforced 2219 alloy, and this one is for the 2219 TIC composite. Okay, so here you could see that the fatigue resistance of the composite is much inferior compared to that of the unreinforced alloy. Okay, and as the plastic strain increases, the difference in the fatigue life also becomes more pronounced. Now let us have a look at the plastic stabilized stress strain loops that develop under plastic strain controlled fatigue. So here again the dotted one is for the unreinforced alloy and the solid curve is for the composite. So here the plastic strain in the composite and in the unreinforced matrix material is equal because this is under plastic strain controlled fatigue condition. But here the total strain in the composite is lower than that in the unreinforced material, although the difference is not that significant as you could see from this figure over here. But the main aspect which is responsible for the inferior fatigue life of the composite is the fact that the deformation in the composite is not uniform. Rather, it is localized, as we have discussed before. So if you look at the strains developed in the local regions of the matrix, especially at the corners or pole of the reinforcement particles, so although the composite is deformed to an equivalent average plastic strain, locally if you see, the regions around the poles or the corners of the particles will be subjected to considerably higher plastic strains. Okay, so this is something we have discussed before also as to how the regions around the particles, particularly near the poles, are deformed differently compared to the regions away from the particles. Okay, so due to such localized conditions, localized deformation conditions, the fatigue life is different for the composite compared to that of the unreinforced material. So therefore, due to such higher plastic strains that develop close to the particles, a higher degree of fatigue damage is expected around those locations. Okay. In addition, the stress strain loop that is developed is considerably larger in the composite material compared to that in the unreinforced matrix. Okay, and this implies that in order to develop a given cyclic plastic strain, the composite material would require more plastic energy or plastic work compared to the unreinforced material. Okay. Alright, so this is where the difference comes from, difference in the fatigue life under plastic strain controlled conditions. One is the localized deformation that you have in the composite due to the presence of the particles and the strains that develop close to the particles around the corners or the poles of the particles. And secondly, the difference in the stress strain loop that is developed in the composite, that also contributes to the inferior fatigue life of the composite. Okay, so this was all about the strain controlled fatigue behavior of metal matrix composites. So while talking about the fatigue properties of metal matrix composites, we first discussed about the stress controlled fatigue And in this case, we have seen that the fatigue resistance of the composite is generally better than the unreinforced matrix material. And the difference of fatigue lives between the composite and the unreinforced matrix depends on the value of the stress ratio R. So when R is equal to -1, that is fully reversed loading condition, we have seen that the fatigue lives differ most prominently in the intermediate stress range. Okay, and the difference in the fatigue lives is not significant at low and high stresses. All right. On the other hand, when R is positive or close to 0, for example, when R is equal to 0.1, the most significant differences are found at low stresses. Okay, so this is what we have seen in case of stress controlled fatigue of metal matrix composites. Now in this lecture we discussed about the strain controlled behavior, strain controlled fatigue behavior. And here we have seen that the fatigue resistance of the composite is generally inferior compared to the unreinforced matrix material. So in case of strain controlled fatigue, we considered two cases. One is total strain controlled fatigue, and in this case we have seen that the inferior fatigue resistance of the composite arises from the fact that the total plastic strain in the composite is higher compared to that in the unreinforced matrix material, and that comes from this particular equation. Okay, so this equation says that the total strain range is equal to the sum of the elastic strain and the plastic strain. Now in the composite material, because of its higher elastic modulus, the elastic strains are lower, and as a result of this the plastic strains will be higher because we are talking about a total strain controlled fatigue test. Okay, so due to the higher plastic strains in the composite, the fatigue damage is higher, and as a result of that the fatigue resistance is inferior. Okay, and then we also talked about plastic strain controlled behavior. Here also we have seen that the fatigue resistance of the composite is inferior. Okay, and that can be attributed to localized strains. As we have seen before, the strains near the poles or ends or corners of the particles will be higher, and as a result of that the deformation in these locations due to fatigue damage will be higher, and as a result of that the fatigue resistance as such, the fatigue resistance of the composite will come down compared to the unreinforced matrix material. All right, with that we come to the end of this lecture. Thank you for your attention.